Hi, my name is Brian Caffo, and this is a lecture on variability as part of the Statistical Inference Coursera class, which is part of the data science specialization from the Johns Hopkins Bloomberg School of Public Health Department of Biostatistics. This class is co-taught with my co-instructors Jeff Leake and Roger Peng. So in the last lecture, we talked about the population mean, which talks about where the distribution is centered at. So if you were to think about a bell curve, that probability density function will move to the left or the right as the mean changes. Another useful property is how fat or how thin, or how spread out or how concentrated the density is around the mean, and that's the variance. So if x is a random variable that has mean mu, the variance is exactly the expected squared distance the random variable is from the mean. And I give the formula here. There's a nice shortcut one that is the expected value of x squared minus the expected value of x quantity squared. So densities with higher variance are more spread out than densities with lower variances. And the square root of the variance is called the standard deviation. So the variance is expressed in the units squared, whereas the standard deviation is expressed in the same units as x, which is quite useful. In this class, we won't spend a lot of time calculating expected values, either means or variances of populations by hand, but I want to go through one such calculation. If we were to use our shortcut formula, recall from the last lecture, the expected value of x is 3.5 when x is the result of a toss of a die. The expected value of x squared, I really haven't given you a formula how to do that, but really think of it as the expected value of the random variable that you get by rolling a die, then squaring the result. And you can do that by simply taking the number, for example, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and multiplying by their associated probabilities, and you get 15.17. So if I were to subtract 15.17 minus 3.5 squared, I get 2.92, which is the variance of a die roll. Since that was so much fun, let's do another example. So imagine the toss of a coin with the probability of heads of p. We already covered that the expected value of a coin toss is p from the last lecture. And then let's think about the expected value of x squared. Well, in this case, 0 squared is 0 and 1 squared is 1, so the expected value of x squared is exactly the expected value of x, which is p. And if we were to plug into our formula, we then get p minus p squared, which works out to be p times 1 minus p. So in other words, the variance, the population variance associated with the distribution given by the flip of a coin, a biased coin, is exactly p times 1 minus p. This is a very famous formula, and I'd recommend that you just commit it to memory. Here I'm giving you some examples of densities, population densities, as the variance changes. The salmon-colored density is a standard normal, which has variance 1. As I go up, you see the variance increases. It squashes the density down, and it pushes more of the mass out into the tails. So there's more likely that a person, say, is beyond 5 if, for example, they're from the normal distribution with a variance of 4 than if they were from a normal distribution with a variance of 3. So just like the population mean and the sample mean were directly analogous, the population variance and the sample variance are directly analogous. So for example, the population mean was the center of mass of the population. The sample mean was the center of mass of the observed data. The population variance is the expected squared distance of a random variable from the population around the population mean. The sample variance is the average squared distance of the observed observations minus the sample mean. So we do divide by n minus 1 here in the denominator rather than n, and I'll talk about why in a minute. But I also want to talk about a conceptually, for me, kind of difficult point, which is to talk about the variance of the sample variance. So let me remind you that the sample variance is exactly a function of data. So it is also a random variable, thus it also has a population distribution. That distribution has an expected value, and that expected value is the population variance that the sample variance is trying to estimate. And as you collect more and more data, the distribution of the sample variance is going to get more concentrated around the population variance it's trying to estimate. And then I also simply want to remind you that the square root of the sample variance is the sample standard deviation. Imagine if I were to do the following. simulate 10 standard normals, and take their sample variance, and do that over and over and over again. Then I get a distribution of sample variances. And that's exactly the salmon colored density right here, is if I were to repeat that process thousands and thousands of times. What I was talking about, the result I was talking about on the previous slide, is merely that this distribution, if I were to sample enough of them, its center of mass will exactly be 1, the variance from the original population that I was sampling from, the standard normal, which has variance 1. The same will also be true for sample variances of 20 observations from this distribution. So I sample 20 standard normals, take their sample variance, and then repeat that process over and over and over again to get an idea about the distribution of sample variances of 20 standard normals. And then I get this more aqua colored distribution, that's the second one, and it is also centered at 1. The same thing when I do it for 30. But notice what happens. The variance, the population variance in the distribution of the sample variance gets more concentrated as I have more data. So in other words, saying that more data is going to yield a better, more concentrated estimate around what the sample variance is trying to estimate. In this case, they're all trying to estimate 1 because they're samples from a population with variance 1. Recall that earlier on in the lecture, we found that the variance of a die roll was 2.92. So imagine if I were to roll 10 dice and take the sample variance of the numbers that were on the sides facing up. Then if I were to take those 10 dice and repeat that process over and over and over again, then I would get a very good idea about the population distribution of the variance of 10 die rolls. I would have to do it a lot, but fortunately on the computer I can do it thousands of times, which is what I did right here. And notice that the distribution of the variance of 10 die rolls is exactly centered around 2.92, the variance of the population of a single die roll. And as I go to 20 and 30, it's still centered in the same place, but it becomes more concentrated about what it's trying to estimate. What this is basically saying is that the variance is a good estimate of the population variance. That as we collect more data, the distribution of the sample variance gets more concentrated about what it's trying to estimate, and that it's centered in the right place, in other words, that it's unbiased. This unbiasedness is why we divide by n-1 instead of n. That makes it unbiased. So now we've talked a lot about variances and even touched a little bit on the distribution of sample variances. Now let's talk again about the distribution of sample means. So remember that the average of numbers that are sampled from a population is itself a random variable. It has its own population mean and population variance. We know that that population mean is the same as the original population. We actually also have a result that relates its variance back to the variance of the original population. In fact, it's sigma squared, the variance of the original population, divided by n. So the variance of the sample mean decreases to 0 as it accumulates more data, which is exactly what we know, that the mean becomes more concentrated as we collect more data, more concentrated about the population mean that it's trying to estimate. This is very useful because we only get one sample mean in a given data set. We don't get lots of repeated versions to investigate its variability the way we do in these fabricated simulation experiments. So we can estimate sigma squared, and we do know n, so we actually know quite a bit about the distribution of the sample mean from the data that we observe. So the square root of the statistic is sigma over square root n, is called the standard error of the mean. And we use this notation, we call a standard deviation of the distribution of a statistic, we call it a standard error. So we talk about the standard error of a mean to imply a number that represents variability of means. And the standard error of a regression coefficient talks about the variability in regression coefficients. So let's summarize because these concepts are rather difficult. So imagine a population that has mean mu and variance sigma squared, so measure of spread sigma squared. If we were to draw a random sample from that population and take the variance, that is an estimate of sigma squared. If we were to take the mean, that's an estimate of mu. However, s squared is itself a random variable and it has a distribution. We don't know much about that distribution, but we do know one thing, it's centered around sigma squared, and it gets more concentrated around sigma squared the more observations that are going into that s squared value. We know a little bit more about the distribution of sample means from that population. We know that they're centered at mu, and we also know it gets more concentrated around mu as more observations go into the means. However, we also know exactly what the variance of the distribution of sample means is. Namely, it's sigma squared over n. Now, in a given data set, we don't have repeated sample means to estimate this, but what we do is we have repeated draws from the original population in order to estimate sigma squared. So the logical estimate of the sample variance of the mean is s squared over n, and thus the logical estimate of the standard error is s over square root n. This quantity right here, s over square root n, is so important it's given its own name, the standard error of the mean, or the sample standard error of the mean. So s, the standard deviation, is really an estimate of how variable your population is. S over square root n, the standard error, is really talking about how variable averages of random samples of size n are from the population. So let's go through some simulation examples. Standard normals have a variance of 1. Then that means they have a standard deviation also of 1 because the square root of 1 is 1. So means of n standard normals, if our math is right, should have a standard deviation of 1 over square root n. So let's say my number of simulations is 1,000, my n is 10, and here what I'm going to do, you can sift through this code a little bit, but let me tell you the gist of what I'm doing. When I simulate R norm, number of simulations times n, I'm simulating 1,000 times 10 draws from a random normal distribution, and I'm arranging them in a matrix. And then with 1,000 rows and 10 columns. Then for each row, I'm calculating the mean. Thus, each row is the mean of 10 IID draws from the standard normal distribution. Okay, and I've done that lots of times, so when I take the standard deviation of this should be a good approximation of the standard deviation of averages of 10 draws from the standard normal distribution. And if you don't think so, then maybe add a couple extra zeros to the number of simulations, but not too much because your computer will get stuck. So if you do that, you get 0.31 or around 0.32. If you just take 1 over square root n, that's 0.31 or around 0.32. So they have to be the same. Let's try it again. Standard uniforms, remember that density that's a flat line between 0 and 1. That turns out that has a variance of 112. So let's take means of random samples of n uniforms. So what we're going to do is we're going to simulate, in this case, 10 uniforms, take their average, and then do that over and over again, and then take the standard deviation of the collection of averages of 10 uniforms. And that will tell us about the distribution of averages of 10 uniforms from this population. Our math says that it should be 1 over square root 12 times n. So if we do this, we get 0.09, and if we just take 1 over square root 12 times n, we get 0.09. Poisson's 4 have a variance of 4. So Poisson is a distribution that we'll cover later on in the class, but for the time being, just think it's a discrete random variable that happens to have a variance of 4. So means of random samples of n Poisson 4 then must have standard deviation 2 over square root n, according to our rule. Okay, so here I do it, and I get 0.62 when I empirically simulate lots of averages of size 10 of Poisson 4s, and I take the standard deviation of thousands of them, I get 0.62. If I do 2 over square root n, I get 0.63. So maybe off by a little bit, but maybe beef up the number of simulations, and you'll get it much closer. So let's go through one more example. Remember that coin flips for a biased coin have a variance p times 1 minus p. When p is a half, that gives you a 0.25 is the variance. Means of random samples of n coin flips, according to our theory, should be 1 over 2 square root n, fair coin flips. So what I've done here is I've flipped a coin 10 times and taken the average of the 10 coin flips. Then I do that thousands of times, and I'm going to look at the variability in that distribution. I'm going to look at the standard deviation because I like standard deviations better than variances. And so I get 0.16 when I do that. The theory tells me it has to be about 0.16. When I do 1 over 2 times square root n, I get about 0.16. So again, the only time you'll ever have to do these simulation experiments is in a class like this where you're learning about what the standard error of the mean is actually implying. And so let's actually go through a data example. Here I'm going to use the father-son data from the using R data set, and I'm going to grab the son's height, and n is going to be the number of observations, like always. If I were to plot a histogram of the son's height, I get this distribution right here, and I overlaid the histogram with a continuous density estimate. It's quite Gaussian looking. Now, this density estimate is an estimate of the population density. We don't have the population density because we didn't collect an infinite amount of data. Variability of this histogram, which is what the sample variance is calculating, it's estimating the variability of son's heights from whatever population this was drawn from. Let's assume that it was a random sample. Let's just go through a couple of the numbers we can calculate here. So here I took variance of x divided by n, standard deviation of x divided by square root n, and I rounded all the numbers to 2 decimal places. So 7.92 and 2.81, the variance of x and the standard deviation of x, are simply talking about the variability in son's heights from this data set, which are estimates of the variability, the population variability of son's heights, if you're willing to assume that these sons are a random sample from some meaningful population. I like 2.81 in this case over 7.92 because 7.92 is expressed in inches squared and 2.81 is expressed in inches, so I like to work in the units rather than the units squared. 0.01 and 0.09 are no longer talking about the variability in the children's heights. It's talking about the variability in averages of 10 children's heights. So 0.09 is probably the most meaningful one, and it's the standard error, or in other words, the standard deviation in the distribution of averages of n children's heights. And again, in this case, it's an estimate of that, but it's the best estimate we have from the data that we have. So let's summarize what we know, because we covered a lot of somewhat complicated topics in this lecture. And I would say fundamentally what differentiates understanding statistics from not understanding statistics is understanding variability. So if I were to say what's the most important lecture, it might be this one. So let's summarize what we know. The sample variance is an estimate of the population variance. The distribution of the sample variance is centered at what it's estimating. This is a good thing. This means that it is unbiased. And it gets more concentrated about what it's estimating as you collect more data. Again, this is a good thing. This means if we go to the trouble of collecting more data, we get a better estimate, that the distribution of the sample variance is more concentrated about what it's estimating. We also know a lot about the distribution of sample means. We know where they're centered at from the last lecture, but we also know in this lecture that the variance of the sample mean is the population variance divided by n. And the square root of it, sigma divided by square root n, is the so-called standard error. These quantities represent how variable averages are drawn from this population. And it turns out that we can say a lot about the distribution of averages from random samples, even though we only get to look at one on a given data set. And this gives us a lot to work with, and it forms a lot of the foundation of ways in which we can perform inference.